Huzzah! Okay. So I know that you all did your homework, which was to read the description. Wow, that's a nice little movie. Was to read the descriptions of the classification of low dimensional Lie algebras in the document that I linked. So hopefully you looked over that. And I just wanted to, before we go further into things, I wanted to highlight some ideas from that are very representative of the general theory that we're going to see. So notice that one of the things that we did before, one of basically the strategies that came up in that classification was, essentially if we had some Lie algebra, often like time and time again within that classification, what we did is we found some basis and we simply, we analyzed what the result of the Lie bracket was on all of the basis elements, right? And we said if we could match these things up together, that allowed us to produce an isomorphism between some of these Lie algebras. So those of you might remember last time, or I guess a couple sessions ago, I made a definition that of the what are called the structure constants, because if I have, right, if this is a basis for my Lie algebra, then if I take this bracket, right, what I'm going to get is just some other element in my Lie algebra. So sum up from, maybe I'll call this n, k equals 1 up to n of, well, it's going to be just be these other vectors here, b sub k, and I'm going to have some constants. Well, let me give these constants some names because I'm going to have a different constant for each k, right? So I better denote this by k. But this also depends on which vi and the I and j that. So we get these constants c sub I j k, which are defined exactly to be the coefficients when you get them, right? So these are the structure constants. Right, and you'll notice that as you looked at the presentation, we have different bases that have like different structure constants, right? So one set of structure constants isn't unique to a choice of basis, right? But what we were implicitly making use of in that document is that if I found some other Lie algebra, or if I found some other basis for my Lie algebra, say with structure constants given by, let's call it, let's use these, this other basis. Well, if it's the case for all I, j, and k, if all my structure constants are equal, then, well, maybe I should say, so maybe I'll call this H. So up here, I'm doing this for a Lie algebra G. Down here, I'm doing this for a Lie algebra H. If all of these are constants, then I can define a map by simply taking Vi to Wi and extending by linearity. And this will give me an isomorphism if I do this, right? So implicitly, that's a fact that we're using. If you like, I mean, you can prove this formally just by checking, well, the definitions of isomorphism, making sure that it, I mean, what do you need to do? You need to make sure that this map is an isomorphism of vector spaces. Well, this is always the case. If you pick a basis of one space, a basis of the other that are the same size, and you simply map basis vectors to each other, that's a isomorphism of vector spaces. And the only thing that you need to check is that it preserves the Lie bracket on both of these spaces, but that's exactly a consequence of the fact that the structure constants match up. Also, something that was particularly important was we looked at, given some x in G, we looked at this map add x, right, which was a linear transformation from G to G. So that sent y to x bracket y. This is the bracket of G. Yeah, in particular, right, if we choose, right, so actually, I wanna, yeah, I'll say, so if we choose a basis for G, we can think of or represent add x as an element of GL, the dimension of GC, right? So this is basically, right, it's a linear transformation on this vector space G. So if by picking a basis, we can represent all of those as n by n matrices, where n is the dimension of, right? So this is GLC n, right? So remember, this is the Lie algebra. This is the Lie algebra, which is just all dim G by dim G matrices, where the Lie bracket is just given by the difference of matrix multiplication. So this actually suggests a little bit more of a general definition. So given a vector space V, GL V is the Lie algebra of linear transformations where the Lie bracket is just given by the difference of composition, right? We also sometimes write GLV equal to n, right? We call these endomorphisms of the vector space. It's just all linear transformation. So, moving over to the other board. Camera. Yeah.
Question about the GLDIPC and this might be a misconception, okay, but would we need them to be invertible matrices or no?
Nope. Okay. No. So there's the group GLN. I shouldn't say C because we're talking about real and complex field. So there's a group. Let me just work with C here. There's the Lie group GLNC, and this is n by n invertible matrices. Right? These are uppercase letters. And then this is the MathFrac font GLC, which is its, so this is a group. In particular, it's a Lie group, which we didn't really talk about. This is a Lie algebra. And this is just all n by n matrices. Yeah, and so here this is a group under multiplication of matrices. Here this is a Lie algebra under the Lie bracket of taking the difference of multiplication.
Oh, matrices. The bottom one is just all endomorphisms.
Yes.
And the top one is bijective endomorphisms.
Yes, exactly. Okay. Yeah, so here we want all endomorphisms for the Lie algebra. Yeah. And in particular, maybe that. So in particular, not only, so given some x in G, we can study, like, we can just take this linear transformation, right? And that told us some things, like that was very useful thing to do in this classification, is to look at, you know, the eigenvalues, for example, or diagonalizability of this linear transformation. But this isn't the process of taking, right? So what have we done? We've taken an element of G and we've really produced something in GL of G, right? And so you might stop and wonder, well, this is so like the map from x to add x is a function, but this is a Lie algebra, and this is a Lie algebra. So maybe this is stronger than just a function, and in fact, so theorem, this is a you know, x to add x is a homomorphism of Lie algebra. So what you need to do to check this, you need to check that, well, if you take add, if you compose these, right? If you apply your Lie bracket first in G, and then apply add, that better have the same effect as first applying your map add. So taking add x, add y, and taking that in the bracket in the Lie algebra here. Right, but that is just add x composed with add y minus add y composed with add x. And if you, so we can test this, so let Z be in our Lie algebra, then add x, y of G applied to Z is by definition, you take this thing, and I'm gonna drop G. When I drop the G here, I just mean the Lie bracket. We get this. What's the other thing equal to? Plug Z into that side. Well, this is I mean, add yz is just the bracket of yz, and you bracket that with x on the left. Minus y xz. And I claim that these two expressions are equal via the Jacobi identity. So that's kind of like also more powerful, right? So not only did we have these maps, which were useful for us to study, but it's even the process of taking an element and producing such a map is now somehow meaningful or more structured, right? It's actually a homomorphism. This, in turn, suggests a more general definition, right? So here we chose some particular process of going from some particular Lie algebra to GL of some particular Lie algebra. And naturally, one might think, well, maybe there's other ways of doing this that are useful, especially if you have been to seen some representation theory before. And so a representation of a Lie algebra G is a vector space V, or I should say maybe is a pair V rho where V is a vector space and rho from G to GLV is a Lie algebra homomorphism. Am I done defining this object for you? No. You should be unsatisfied. Why?
Yeah, be telling us what the homomorphism is.
Exactly. I should be telling you, well, no, not what this homomorphism actually does. But rather, if I define an object for you, I claim that I'm not really done until I've told you what the morphisms of that are. Because the morphisms are what essentially tell you what is the structure you should care about. Right. Exactly. Exactly. So a homomorphism of representations, say V rho to W sigma is, well, what should it be? Representations are a pair, right? There's two pieces of data here. Somehow I should come up with a definition that does something with both of them. Well, let's look at the first coordinate first. What are V and W?
Vector spaces.
They're vector spaces. Yeah. So what should part of the data of my map be then?
Linear transformation.
Yeah, linear transformation, right? I have these two pieces of data. One part is the vector spaces, so probably if I'm going to relate those, probably it should be a linear transformation. So is a linear transformation phi from V to W such that now we need to satisfy the other thing. So it might help if I draw, I'm going to erase some of what's on this board already. And I'm going to draw a picture. So let's think about this. For each X, right? So I've got a map, right? V is a map here. And I have a linear transformation here.
Oh, would it be phi rho x is equal to rho of 5x?
Well, you got the right idea.
Yeah.
Right? So same thing like with the Lie algebra Greek or group homomorphism or something, it shouldn't matter whether we do the operation before or after, right? The problem is, so rho x is defined here, the problem is, once you take phi of x, so I agree with you that if we go, say, row x, so phi of row x should be equal to something. Oh, but the problem is, if you go phi x first, now we're in W.
You have to do sigma.
Yes, exactly. So, the short way, there's sort of a nice diagrammatic way to say that sigma of phi x, that these are equal, right? And so we say that another way to say this is that this diagram commute, right? By that I mean follow the composition of maps along one path of arrows, follow the composition of maps along the other path of arrows, and those will agree. Yeah.
The x is in the wrong place on the right side because phi is not a function that picks things in the group.
Oh, sorry.
Sigma of x composed with phi.
Right. What have I done? Composite. Yeah, there should be composition, right? Right. There should be composition of maps. Sorry. Yeah. Thanks. Yeah. Sigma.
Sigma of x.
Sigma x. Yeah. Composed. Right. Another way to say this is that for all v in V, row x applied to V, and then you apply sigma is equal to, or phi is then sigma of x applied to phi. Yeah. So 3 different ways of expressing this. Thanks. Okay, so I know we've kind of been talking about abstract stuff, but soon we're going to come back to some very concrete things. Let me say, before we do, let me say that, remember last time, or a couple times ago, I gave you the definition of a Lie algebra. And I said, look, we have an algebraic object. You should immediately start thinking, I made this list of tables, right, of all these objects that had all these things, right? Groups, we had kernels, we had kernels, we had sub-objects, we had quotients, we had direct sums, right? And then there was the same thing for rings, and there's the same thing for vector spaces, and then I said, come up with what you think should be the corresponding objects or the corresponding concepts for Lie algebras. I've just defined for you a new algebraic object, right? Together with maps between them. And so immediately, what you should be doing is asking yourself, okay, I've got these homomorphisms. What are those images like? Does it have kernels? What are sub-objects of representations? How can I glue these representations together? Is there a notion of direct sum? So go back and look at that table if you have it in your notes and ask yourself all of the same questions. So homework, ask yourself all the algebra questions. Also, remember what we did for Lie algebras, right? The very first thing we did is we tried to ask ourselves, can we come up with the stupidest Lie algebra, right? And we found that, yeah, we can come up, the zero-dimensional vector space with the trivial Lie bracket, right? And then, so next thing you want to know, well, do any representations exist? Well, yes, we know. I mean, I told you the adjoint representation is representation, but can you always write down a stupid representation, a trivial representation, right? Then ask yourself, just like before, like take a Lie algebra and ask yourself, so we can always write down maybe a trivial one of the trivial Lie algebra or something. Then take any Lie algebra, ask yourself, can I always write down a stupid representation for it? And then try and come up with some non-stupid representations. So this is all a good bit of homework, and I think it's really good to try and do all this on yourself and ask yourself, well, how would I define kernel? How would I define this and that? And really work at it on your own, and then see if your opinion matches up with the opinion of other mathematicians. Okay. Yeah, a couple interesting things I wanted to point out in the classification. Any questions? I guess I should pause. So let me just remind you that in the classification of the case when this was dimension 3 and what was called the rank 2 case, this was dimension 2. Specifically, well, in that paper, I think they only work with real Lie algebras, but we focused on some particular element X, and we looked at the case when we had an isomorphism here. And there was basically 3 cases. So we had that this as a linear operator had distinct real eigenvalues. Lambda 1 and lambda 2, where we were able to come up with a basis that had the following operations, or the following brackets. And we had another case that was real eigenvalue lambda. I don't think I wrote that one down, but it's fine. We don't need it. Of multiplicity 2. And we also had well, maybe I also want to talk about Fulton and Harris focus more on the complex case as well. So I'm going to look at the complex Lie algebra with this multiplicity 2. And one thing I just want to point out about these is this gives us a very sort of motivation for the idea of what a mathematician might call a coarse moduli space. There's maybe, different notions of this, and there's very fancy definitions in terms of functors and categories and blah, blah, blah. But the rough idea is that you want to classify objects, and you want to classify them with points in some geometric space. So points in some geometric space X correspond to objects parameterized by this little X. So one thing, for example, in this case, we found that these Lie algebras were isomorphic. So we had a Lie algebra depending on X, and these two were isomorphic if and only if X was equal to Y or X was equal to Y inverse, right? So that means that geometrically, right, you can take your Lie algebra, if X was greater than or equal to 1, then what you could do is just take x inverse instead, and now you have a number that's less than or equal. So basically, what that means is that every point, so we weren't allowed to have 0, and we weren't allowed to have x being equal to 1 or minus 1 because here, sorry, x in this case was equal to lambda 1, right? And so here, what's interesting is we actually get a parameterization, right? The points in this space correspond to the algebra. Which is just an idea that I absolutely love. And we can sort of imagine, right, the case when lambda 1 equals lambda 2, that's somehow like the boundary point here, right? So it's not part of this classification, but if you actually approach either boundary point, this is somehow like this, that corresponds to this special case where they end up becoming equal. And so we can actually think of these, you sort of imagine this geometrically, we can sort of go the other way and glue these two things together and really just think about it as a single connected segment, but there's maybe some sort of like singular points that we pass through here, which is sort of realizes this degenerate version of this. So this is not important to the general theory necessarily, but it's just an interesting idea that comes up a lot in mathematics, parameterizing objects by points in the geometric space. And sometimes the geometry of that space can have an impact on the objects themselves. And that's actually kind of the central idea in my research. So in Fulton and Harris also talk about, they talk about the case specifically for like, for complex, for these Lie algebras with the complex numbers. And again, you get a parameterization in terms of these complex numbers, where now alpha is some non-zero complex number. So again, we can imagine that as being just parameterized by points in the punctured unit disk. Anyways, let's get a little bit more concrete. Wow, we're almost out of time. That's fine. So let me write down some very concrete examples of Lie algebras that are important. Can I get a camera image? So there's good reasons why this isn't just an arbitrary naming convention. We will have some explanations for this, but there's SU2, which is the real span of these three matrices. So this is all real linear combinations of those three matrices. There's FL2R, which is the real span of these three matrices. And there's also SL2C, which is the complex span of the same three matrices, but now as a complex. So one thing I want to, and of course, our Lie bracket is just given by the normal Lie bracket that we use for matrices, right? A times B minus B times C. What's interesting about this is that even though we write it with complex numbers in the matrices, this is a real Lie algebra. It's not a complex Lie algebra. right? This has 3 dimensions as a real vector space. Right? This is dimension 3, as is this Lie algebra. And and there's a special relationship that maybe by the end of the summer we'll be able to say something about, but it turns out, so there's a special relationship between these, and maybe we'll talk about this a bit more later, but it has to do with the idea of complexification. Well, I might tell you about tensor products in the last 10 minutes. So the process of complexification basically takes a real vector space and produces for you a new vector space over the complex numbers, which maybe some of you don't know what this means yet, and we'll talk about it. The way that you do it is you take a tensor. So that's one use of tensor products. But then there's also a sort of forgetting, right? I mean, if you have, suppose you have a complex vector space like C2, right? C2 has a basis, just the standard basis, right? But now what we can do, because this is a basis with respect to complex scalar multiplication, right? So everything can be written as A plus BI, C plus DI. But now I could factor this out, right, into A10 plus B0I plus C10 plus or sorry. I have 2 coordinates. What am I doing? Yeah, plus D0I, right? Sorry, this should be I in the first coordinate. Right, this should be I in the first coordinate. This should be 1 in the second coordinate. This should be I. Right? But now A, B, C, and D are all real numbers. Right? And so now I can forget that this ever was a complex vector space. And so if I have a right an n-dimensional complex vector space in this way will give rise to a real vector space of dimension 2. Right? So in particular, there's it turns out that the way that both of these are related to this is through the idea of complexification. And I don't even know. Yeah, maybe we'll get to talk about it, but this is a sort of deep and important idea where these are called forms of SL2C. And this one is the compact form and the non-compact form. But I don't know if we'll actually get to really dig into that. One other thing I wanted to mention is that, by the way, there's something else, there's another Lie algebra called SO3, which happens to be isomorphic to SU2, which is a very sort of, it's an important accidental isomorphism, as we sometimes call it, which is actually relevant to physics and to different phenomena in physics. And in particular, this is also, it's also the Lie algebra of the real numbers together with the cross product. So the cross product actually turns R3 into a Lie algebra. I don't know if I mentioned that before. Okay. So in the last little bit, I guess, what do I want to say? I'm gonna mention a couple definitions here. And then we sort of need to make another decision about where we're going to go, but I think that just involves some reading and stuff. Maybe I'll talk about that once I end the recording, or where we'll go next, we'll have a conversation. So, for those that don't have to run immediately. So let me just say this, there's one idea that we hit upon, what I think was last time, Nestor, you mentioned the simple Lie algebras, and can you have Lie algebras that aren't simple and aren't, decomposed as a direct sum, for instance. So, yeah, let me just maybe remind you, one other thing that happens, that happened in here, right, is we sort of, remember, we realized that the abelian Lie algebras those were sort of boring, and if you found that you had some Lie subalgebra and H was abelian, you could do something like quotient out G by H, and just sort of kill that abelian part and then study the non-abelian piece of it, right? Or we also in the classification went the other way around, and we had like the commutator subalgebra. And that was sort of the biggest thing, or rather the smallest thing that we could find, so that this would be an abelian quotient. And that was another way to look at it too, was, well, let's take this sort of largest chunk inside of here, right? Oh yeah, so an important thing I want to point out is notice that in all of these cases, right, these all came from the dimension 3, rank 3 case. So our commutator algebra was the entire thing. This is going to be an important idea to remember for later on. So in particular, remember what that means. This is the largest abelian quotient, right, that we can find. So in particular, in these cases where the commutator subalgebra was G, that means the largest abelian quotient we could find was just trivial. So these are, there's not so much, there's no abelian, there's really no abelian quotients there to find. And this leads to two ideas. So one, a Lie algebra, right? A Lie algebra is simple if it has no non-trivial ideals. All right, and this is very similar if you've studied some group theory, very similar to the idea of a simple group, right? Although here, yeah, so the analog of an ideal here would be a normal subgroup, right? And this makes sense, right? Like, how do we try and understand these Lie algebras? Well, if it's got some sort of abelian, like some sort of thing inside of it that we could quotient out by, then we could look at the subspace and we could look at the quotient, and then ideally we'd be able to, pun intended, glue that information back together and understand the original Lie algebra, right? There's one in between thing here that happens that I suppose you could argue in certain ways it happens for groups if you talk about like an extension of an abelian group or something, but we get this in between case where we also have a definition called semisimple. And semisimple is when it has no non-trivial abelian ideals, right? And so, it's sort of this in-between step where it's like, let's allow for ideals, right, which are subalgebras, but we're gonna make sure there's no really stupid ones. Because we looked at this classification, and there's some interesting structure, right? Certain algebras, like if they're not abelian, then there's actually something to be said. So we'll call it semi-simple, because we'll allow for some, not so stupid ideals to be. And it turns out that semi-simple, so of course simple implies semi-simple, right? And it turns out that the classification of semi-simple Lie algebras has a really nice, beautiful theory to it that's like quite powerful and elegant. And that's something that we might focus. One last thing, does anyone have to run right away? Actually, should I save that? Maybe I'll save this for next time. It's already 1:55. I was gonna talk about the wedge product and tensor product. But maybe I'll talk about those next time. I don't. Yeah, so I guess I'll end the recording there.